Alright, welcome everyone to this video. We're going to continue our discussion on Gibbs free energy and talk a little bit more about its temperature and pressure dependence. Okay, so we showed in the previous video how some change in Gibbs free energy is related with the change in pressure and change in temperature based on the volume and entropy. Okay, so let's consider the temperature dependence of the Gibbs free energy under constant pressure. Okay, so under constant pressure, dg equals minus s dt, okay? Or rewriting that, the partial derivative of g with respect to temperature, constant pressure is equal to minus s, negative of the entropy, okay? So using the fact that the Gibbs free energy is equal to h minus ts, okay, rewriting that, that entropy is equal to h minus g divided by temperature, okay, which is equal to negative dg dt from this relationship above. Okay? So just rewriting that equation, okay, multiplying through by the minus signs, you get g minus h divided by temperature equals dg dt. Okay, if we subtract g divided by t from both sides, okay, you will have negative h divided by t equals dg dt minus gt. Okay. So far, this equation doesn't really look like much, okay? But if I use the fact that the derivative of g divided by t with respect to t is equal to 1 divided by t times dg dt minus g over t squared, okay? And I use this relationship and divide the top equation by t squared, I get that minus h over t squared equals 1 over t times dg dt minus g over t squared, which just equals the derivative of g divided by t with respect to temperature. Okay, and so we get this relationship, which is called the Gibbs-Helmholtz equation. Okay, which is relating how Gibbs free energy changes with temperature under constant pressure and how it's related with enthalpy. Okay, and you can rewrite this equation similarly in a different way, where the enthalpy is equal to the derivative of g divided by t with respect to 1 over temperature. Okay, so you're just rewriting some things, you can show that these two equations are equal to each other, And so writing it this way shows that under constant pressure conditions, if you plot 1 divided by the temperature with respect to the change in Gibbs free energy divided by the temperature, okay, under constant pressures, the slope will get you the change in enthalpy, okay? All right, and so, if we think of how Gibbs free energy changes with constant temperature, okay, at constant temperature, dg equals vdp, okay? If we think of solids and liquids, that volume is effectively constant with pressure, okay? We're taking, and that's related with the isothermal compressibility, cap sub t, minus 1 over v del p under constant temperature, and this is typically a very small number for both solids and liquids, so the volume is effectively constant with temperature, and so basically for solids and liquids, under constant temperature conditions, the Gibbs free energy increases with an increase in pressure, and it's related by the volume of the system. Okay, we look at for gases, if we consider an ideal gas, then we have that the volume of the ideal gas is related to temperature and pressure as such, Temperature, number of moles are being held constant, pressure is the only thing changing. So when you integrate out that equation, G equals nRT dP over P, you get that the change in Gibbs free energy for a gas, an ideal gas specifically, under constant temperature conditions is related with nRT ln P final over P initial. Okay? And so finally, the last thing we're going to kind of talk about in terms of kind of introducing a lot of these thermodynamic quantities is the chemical potential. Okay, so in all the previous videos, recordings we've talked about, we haven't really talked about this chemical potential. Okay, And this chemical potential is related with how the Gibbs free energy or Helmholtz free energy or enthalpy or internal energy changes with change in number of moles. Okay. Now, depending on what it's related to, right, it depends on what is being held constant, right? Temperature, volume, entropy, pressure, temperature, pressure, right? Depending on what things are being held constant, tells you the relationship between the change in these quantities and change in number of moles. Okay. We will often use this definition of the chemical potential, okay, which is again how your Gibbs free energy changes with the change in number of moles, assuming constant temperature, pressure conditions. Okay. And because again that's most related with how our chemical reactions and phase changes and other things are occurring, and so that's most often what we're concerned about. Okay. And we're going to be using this chemical potential a lot in the next couple of sections, chapters, and things that we discuss. Okay, and it will be very relevant and very important.